So we will just see a sample transient simulation for a two input gate. Okay, so CSH, source, home, CAD, CSHRC, and start with virtuoso. So we are going to do a simple transient simulation, and we are going to calculate the propagation delay from the waveforms. File, new, cell view, because we already have the library, and I'm going to say NAND2 for a 2 input NAND gate, and I insert the transistors. I know the library name is GPDK180 and I can type it. So I have two cells, NMOS and a PMOS. So I'll first place two NMOS transistors. That's a NAND gate, and next I will insert two PMOS transistors. Again, just to recall, how do you insert? You press I on the keyboard and see how the cursor changes to insert mode, and you get this window, and you can place your PMOS transistors here and here. And once this is done, let us press I again and place the sources which are available in analog lib, and we need VDC. We put the DC voltage as 1.8 and we keep that somewhere on top because the connection is given there. And another source is V pulse, which is also 1.8 for voltage 2. Okay, and see how you don't put the units yourself, just press 1.8 and press tab. Okay, it will add the V, should add the V, but it will add the V itself. Okay, and 1.8 and press tab. Okay, so period, generally we stick with 10 nano. Delay time we don't care. Okay, rise time and fall time both are at 10 pico, and pulse width, period, you can go for 5 nano. 10 is fine, and then pulse width we will give lesser than the period, which is 5 nano. Okay, and this is the pulse, and we have 2, right? So I will place 1 and I will insert again, and I will 1.8, that is the same period. Okay, let it be 10 nano, and rise time is 10 pico, fall time is 10 pico or 10 seconds, but this time I'll give the pulse width different. So let me give it as something like 3.2 nano. Okay, why I'm giving this different? Otherwise both pulses will be the same and I will not get to see different combinations other than 0 1 0 0 and 1 1. So I want to see 0 1 1 0 also for the input. And the last thing we need, of course, is the ground. That is also in analog lib library, and we can place many grounds just to keep the connection simple. We don't have to have only one ground. You can have 10 grounds, and the simulator knows that they're all the same. Okay, and lastly, for connecting the wires, we will use the key W. Okay, and I will make one connection like this and connect this to the top, connect this below. Okay, and these two get connected together to the NMOS transistor, and NMOS are in series, that comes here and goes to the ground. And the fourth terminal, the easy way to remember the fourth terminal connection is just to remember that wherever the transistor is, whatever type it is, connect it to the terminal with the arrow. So if you zoom in here, okay, the transistor has two terminals, one of them has the arrow. Okay, so we just need to make the connection from the fourth terminal to the arrow terminal. Same thing when you come down also, fourth terminal to the arrow terminal, that's all. And the same thing here also, fourth terminal to the arrow terminal and fourth terminal to the arrow terminal. So this will make sure that you are connected the fourth terminal also properly. And finally we have the input. You can call this input A and B, for example, and one input should be given to one PMOS transistor and one NMOS transistor, and the other input should be given to the second PMOS transistor and the NMOS transistor. So again, if you double click on a wire generally, it will show you where all the wire is going. So it's going here and here. Similarly, if you do it for this wire, okay, so it's going from here to this transistor and this transistor, and all the other things are complete. We have given the values for the VDC, we have given the values for the V pulse also, and the connections are complete and ground is there. And once it is all over, always we do a check and save, and we didn't get any messages, which means that the circuit is fine. Then we can go for the simulation using launch ADEL. Get this window, analysis, choose transient analysis. You can give 50N is fine because we have a pulse width of 10N. You'll see 5 cycles, and then outputs to be plotted. Select on design. So here, okay, we want to see the inputs. That is, this wire is one, this is the other input, is going to these two, and then the output is available at this particular wire. So I select that, and I can see those three have come here, and then I do the simulation. So once I do the simulation, I separate, okay, and the thing to remember always is that the levels, okay, should be at 1.8 and 0. I mean, this is, it is showing 5.1 micro, that is fine, that is equivalent to 0, no problem, okay. But values of 200 millivolt, 400 millivolt are all not acceptable. They should be at perfect values. And we see these spikes here because suddenly both inputs are changing at the same point, okay. If you want to leave that, that's fine, that's not an issue, but I do want to change that. And the simple way to change that is to change the period to say 8, okay, and do a check and save and simulate again. It is not a mistake, but I don't want to see the waveforms like that. Now this is even worse, so I'll go back and again press Q. We'll go back to the old one itself. I think that seemed better. Okay, check and save and simulate. That's all. So let me now separate all the waveforms and click on each of these and place a marker. This is a type horizontal marker, and it is at 0.9 because that is a 50% value. And I do the same on all the three graphs, 0.9, and finally click on the third one, create marker, 0.9. So now I want to calculate, for example, here, okay. um, okay, this is a good situation. Let's say I want to calculate TPHL on this waveform, okay. The input output is going from low to high, so it is TPLH actually. Now there are two waveforms. This is the input waveform, this is the other input waveform. So you might ask, where is the 50% number to take? This is happening much before. This transition is not causing the output to rise. We want to find out which particular transition is causing the output to rise here, okay. So this is one transition that might have caused it, this is another transition that might have caused it, and the right answer is this one. So if you're calculating TPLH, it will be 33.2477 minus 33.215. So I will just write that down here for my reference. Okay, so 33.2477 minus 33.005. And how much is this? I will calculate that. 33.2477 minus 33.005 equal to, sorry, it's a mistake, not 33.005. I should take 33.215. Sorry, not 005, 215. That is 33.2477 minus 33.215. I'll calculate that again. 33.2477 minus 33.215. is equal to 0.0327 nanoseconds, or it is 32.7 picoseconds. Okay, and then I will go to this waveform where the output is going from high to low. So this is 40.0282, and now both are at the same time, so you can take 40.005 there or 40.005 here, doesn't make any difference. So I will take 40.0282 minus 40.005, and I get 0.0232 or 23.2 picoseconds for TP high to low. Okay, and finally the average number TP equal to TPHL plus TPLH by 2, which is 23.2 plus 32.7, which is 55.9 divided by 2 equal to 27.95 picoseconds. So that is the calculation of the propagation delay for the gate. Okay, so this is one experiment. This you can do for any gate like a NAND gate or a 2 input and 2 input NOR or any other gate. Okay,